KB over 2 something. I don't remember exactly. Was it KB over 2? Somebody can KB over 2. Okay. So that is like a sinc function. So if KB is very large, then it goes very sharp, or KB is very small, it's spread out. KB is small means the wavelength is very large compared with the B. Yeah? Is it true? Am I talking the other way around? If KB is large, that means B is large compared with the wavelength. That means B is large, and I am sending this kind of wave, right? And the KB is small means that B is small, and I said, right? Then it radiates like a monopole, right? B is small, and I push very slowly, and it radiates monopole. When B is large and I oscillate this, then the scattering is heavily occur at the edge. Therefore, the style of radiation would be like this, because there is so many scattered field at the edge. Okay? And then we expand that case to 3D case, and essentially what we obtain is the directional dependency, which would be not only in this direction but also this direction too. So again, I have this kind of window. If the size of window is large compared with the wavelength, that means I am oscillating the fluid like this, then the scattering occurs at all the edges, right? So the scattered field would look like I have a big what I call, what is it, the OE in English? Cucumber. I have a strange looking cucumber, and the small many cucumbers over here that expresses the scattered field due to the edge, the existence of the edge. Okay? So that essentially summarizes the diffraction and scattering phenomena, and I think I succeeded to explain diffraction using scattering. Okay? And also we learned about famous Fresnel number, right? The Fresnel number essentially measures relative distance between the source and observer with respect to wavelengths. Yes, this Fresnel number goes up, transmission loss go up, right? Therefore, we can easily estimate the transmission loss due to the wave. And the formula we just saw is a transmission loss of barrier, and it looked like what? 20 log 10, and in the argument that is like the square root of 2 pi Fresnel number divided by hyperbolic tangent square root of 2 pi Fresnel number. That formula really breaks down when Fresnel number is large or small. When Fresnel number is small, that means what? Wavelength is large compared with A plus B minus D. That means I have a big barrier. For example, the height of a barrier is like 20 meter, but the wavelength is, for example, more than 5 meter. That means the frequency is about 60 or 70 hertz, very low frequency. Then wavelength, because wavelength is 5 meter, that will induce a very severe diffraction. In that case, this formula does not really meet. But if the Fresnel number is high, means that the wavelength is small compared with relative distance between source and observer. Then what will happen? The radiation, the scattered field or diffracted field is mainly due to the radiation from the edge of the barrier, right? In that case, this formula really well represent the physics. Okay. So that summarizes scattering, diffraction, everything. Okay? And then let's move to our final chapter, chapter 5. Okay, chapter 5 essentially handles the space. Acoustic space. Acoustic volume. Or acoustic dimension. For example, when I shout here, or when I sing a song over here, huh? What kind of song you want to hear? Yeah. Any request? Song.
Your favorite song?
Baby song?
Your favorite.
Favorite song. I don't have favorites. Maybe Kang Dong-soo is, he's a famous singer, right, now at university. But suppose I'm singing over here like that. All right. Yeah? And what you can hear is many different frequencies.